Hey everyone, welcome to the channel. Before we dive into today's mind-bending topic, I genuinely hope you're feeling fantastic and healthy. Take a deep breath, get comfy, and let's explore something truly fundamental about our universe together. So, you've probably heard that gravity keeps your feet on the ground, holds the planets in orbit around the sun, and even keeps entire galaxies together. It feels incredibly powerful, right? But here's a jaw-dropping fact. Gravity is actually the weakest of the four fundamental forces that govern everything in existence. It's so weak, it's almost laughable compared to the others. Let's unpack what that really means and why it totally blows our minds. First off, what are these fundamental forces? Imagine them as the basic rules of engagement for everything in the cosmos. There are four of them. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one plays a totally different role. Gravity is the force of attraction between any two things that have mass. Electromagnetism handles anything with electric charge, like magnets sticking to your fridge or light traveling through space. The strong nuclear force is the ultra-powerful glue holding the tiny particles inside an atom's nucleus together. And the weak nuclear force is involved in certain types of radioactive decay, like when atoms break down over time. Now, when scientists say gravity is the weakest, they mean it's ridiculously feeble when you line it up directly against the others, especially at the super small scale of atoms and particles. Think about this. A tiny fridge magnet can defy the entire gravitational pull of our enormous planet Earth. That little magnet sticks to the fridge because the electromagnetic force between the magnet and the metal is stronger than Earth's gravity pulling it down. How wild is that? One small magnet versus an entire planet, and the magnet wins. Let's get even more specific. The strong nuclear force? It's about 100 times stronger than electromagnetism. But compared to gravity, it's roughly 10 to the power of 38 times stronger. That's a 1 followed by 38 zeros. Imagine the strongest thing you can, a supernova explosion, a black hole, and then multiply it by an almost unimaginable number. That's how much more powerful the strong force is than gravity. Even the weak nuclear force, which is the second weakest, is still a billion times stronger than gravity. It's like comparing a single grain of sand to every beach on Earth. So why does gravity feel so strong to us? Why don't we float off into space? It's all about scale and reach. Gravity might be weak, but it has two superpowers the others lack. It works over infinite distances, and it only attracts, never repels. Plus, big objects like planets and stars have enormous amounts of mass. Since gravity acts on mass, and these cosmic giants have so much of it, their collective gravitational pull becomes incredibly powerful over large areas. Electromagnetism, on the other hand, often cancels itself out because it has both positive and negative charges. The strong and weak nuclear forces are locked inside atoms. They don't even reach beyond a tiny fraction of a millimeter. Gravity, though? It just keeps going and going, pulling everything together across the vast emptiness of space. That's why it rules the universe on the big stage, galaxies, stars, planets, even if it's a weakling in the particle world. Here's another head-scratcher. Gravity doesn't play by the same rules as the other forces. Electromagnetism and the two nuclear forces are explained beautifully by a framework called quantum field theory, which deals with particles and waves at the tiniest scales. But gravity? We understand it best through Einstein's theory of general relativity, which describes it as the warping of space and time itself. Picture space as a stretchy trampoline. Put a heavy ball in the middle, and it creates a dip. Roll a smaller ball nearby, and it'll spiral toward the big one, not because of some mysterious pull, but because it's rolling down the curve. That's gravity. Now, scientists are desperately trying to reconcile this with quantum mechanics. Why? Because at the heart of a black hole, or during the Big Bang, where things are both incredibly massive and incredibly tiny, our two best theories clash. Figuring out quantum gravity is one of physics' biggest quests. Even with its weakness, gravity has given us some of our coolest cosmic discoveries. Ripples in space-time called gravitational waves, predicted by Einstein, were finally detected in 2015. When massive objects like black holes collide, they send out these waves that travel at the speed of light, stretching and squeezing space itself. Detecting them was like giving humanity a new sense. We can now hear the universe in a way we never could before. And it's all thanks to gravity's subtle but far-reaching influence. So next time you drop your phone, hopefully not, remember, the force pulling it down is the feeblest of nature's fundamental players. Yet, without it, stars wouldn't ignite, planets wouldn't form, and you wouldn't be sitting there watching this video. It's a beautiful paradox, weak but universal, subtle but cosmic. It's the quiet architect of the grandest structures in existence. And that's why, even though it's the underdog of physics, gravity is absolutely awe-inspiring. Thanks for hanging out with me today. Stay curious, stay kind to yourselves, and keep looking up, literally. The universe has so much more to show us. Until next time, take care and stay healthy.